Okay, let's get started. So just as a reminder, project number 3 is due on Wednesday, October 24th. After today's class, you should be able to do all of project number 3. Are there any questions before we begin? Okay. So, we left off last time about page 658. So we were talking about, or one of the things that we talked about last time was if you have very highly correlated predictor variables, that can cause problems to your model. In particular, as you will see actually more so in Chapter 7, it can cause problems interpreting the effects that predictor variables have on the response. It can actually cause some computation problems as well. And in Chapter 6 of our book, they first start addressing this issue a little bit. And they looked at ways, some very simple ways that one can detect if you have high correlation amongst your predictor variables. And one very simple way is to do what's called a scatter plot matrix. So this is a scatter plot matrix here. Let me get my red pen out. And in order to read a scatter plot matrix, basically just think of the, in this case, the diagonal elements of this matrix-like structure contain our variable names, and the off-diagonal elements contain actual scatter plots. So for example, this particular scatter plot is a scatter plot of age on the y-axis and field goal percentage on the x-axis. To get a sense of what the numerical scales are, notice for age we have to go all the way over to the end, and for field goal percentage we have to go all the way to the top. So what we can see here is that there's kind of a random scattering of points for age and field goal percentage, not really any kind of strong relationship. Let's take a look at a different one. Oh, let's see here. Maybe we could do field goal percentage in minutes per game. And you can see here that, generally speaking, we have the points kind of falling right around that line, showing that there is a kind of a maybe somewhat weak or somewhat moderate positive correlation between field goal percentage and minutes per game. Now, on the other side of this diagonal, for example here, is just a mirror image of what we saw before. So now we have field goal percentage as the y-axis and age as the x-axis. It gives you the same information, just a mirror image. Now, how does this plot produced in R? Well, there's a few different ways to produce plots like this. In particular, what one can do is use the pairs function and use syntax that we're used to. Formula equal ppm tilde your predictive variables of interest, and there's your plot. Another way to do these plots is shown on page 660. So use the scatter plot matrix function that comes in the CAR package. Remember, the CAR package is the package associated with this recommended book for our course, Companion to Applied Regression. That's what CAR stands for. It has a somewhat similar syntax to what we've seen before. Say x equal, and you can't put ppm on the left-hand side of the tilde. You have to put all the variables, predictor and response variables on the right side. Data equal MBA. And this function also allows you to do a few other things, such as, do you want to put a regression line on it? Sure. Let's do a linear model. Do you want a smoother on it? I'll show you what smoother means shortly. And some other aspects that control the smoother. And then diagonal equal histogram. What that corresponds to is you're going to have actual histograms of variables on the diagonal. So here we go. And here's the corresponding plot. Let me go over to Word so I can mark on it. So we see very similar to what we did before with in terms of the black dots. What has changed is notice that now we have a histogram of the ages, histogram of the field goal percentages, and so on. The green lines on the scatter plots are from a simple linear regression model, where I use, in this case, field goal percentage to try to predict age. Again, it's just more as a graphical tool to help you see relationships. The red line, solid red line that you see on the plots is what's called a smoother. And we will talk about smoothers more in Chapter 11. But for now, what you can think of as this smoother gives you a little bit more, how should I say? It gives you a way to understand the relationship between two variables without being restricted to like a linear model or even like a quadratic kind of model and so on. And in fact, there's not necessarily like an actual equation that you can write out for it like what we've seen before for like y is equal to a plus b times x. It's actually a combination of a whole bunch of regression models, and more on that in Chapter 11. For now, what you can do is think of this as just as a way to as the red line gives you kind of a way to see the relationship of what's happening. The dashed lines correspond to 95% confidence interval bands with expected value of y. Overall, in these plots, we really don't see much of a relationship between the predictive variables, which tells us, what we're doing here with our regression analysis is going to work out okay. Again, more about this later when we look at it in more detail. What can happen when you do have high correlation. Let's see now. And also there's this interesting function called TK brush that's in the teaching demos package. And what this allows you to do, you get the scatter plot and actually get a new window that pops up. It allows you, if you notice where my mouse is, I have this little green square. It allows me to highlight certain points on my plot. It allows me to see it through all the different scatter plots in that scatter plot matrix. This is helpful to see the relationships between the variables, not just in the one scatter plot, but across. So we can see, for example, here, for ppm, for large values of ppm corresponding to the a small number of games played. And it's highlighted throughout the plot. And let's see now. Notice that there are some, I don't want to move my mouse here. Notice for the minutes per game in ppm plot, look at where you see some of the red dots. They correspond to high ppm with very low minutes per game. And this is going to address something that I mentioned last time, if you remember from 1 week ago, that some players in our data set are going to be detrimental to our model, and these are going to be ones that correspond to those players who are not regular players, and they just get in the game in what's often referred to as garbage time. When the game is out of hand, nothing's going to really change in terms of the ultimate outcome of the game, and they play a few minutes, but they might score a lot of points. So more on that when we address that issue in Chapter 10, but just foreshadowing here. And lastly, you could also do a correlation matrix, estimated correlation matrix as well. One little change that I made to my program here is instead of having an 8, I have a 9 here to represent all the variables of interest. And we can see from looking at these correlations that there's not really any large correlation between any of the predictive variables, or even with ppm itself. Just to give you a sense of what this means is that, let's take a look at height and MPG. I have a correlation of negative 0.01, suggesting there's not much of a relationship at all. Let's see if that comes out on the plot. So minutes per game and height. So it's where my mouse is right here. This is the corresponding scatter plot. Notice that's just pretty much a random scattering of points. Notice how the regression model is pretty much flat, horizontal. Well, that's is reflected in this correlation. Any questions? Yes, one last final note. Be careful about predicting y outside the range of your data. This corresponds to something that we learned way back in Chapter 1, where we had a case where here's x, here's y. I'm trying to use x to predict y in a simple linear regression model. One variable to predict y. And perhaps we have a scatter plot that looks like this. We have our regression model that looks like this. What this basically means is that we only want to do predictions corresponding to axis between this point and this point. So we would not want to predict x for a very high value or x for a very low value. We want to keep our predictions within the range of our x's. Now, what happens though when you have more than one predictor variable? How do you judge the range of where you can make your predictions from? Any thoughts? Should you maybe just focus on the minimum? Let's consider a simple case. We have x1 and x2. Should we maybe only consider the the minimum value of x1, maximum value of x1, also the minimum value of x2, maximum value of x2 as our range? Or are you thinking maybe that's a trick question? Well, it's not a trick question, but I'm just trying to help you learn here. Consider the following situation. Notice I do not have y in the plot. I don't really need y. Here's a scatter plot of x1 through x2, of x1 and x2. So we can see the minimum value of x1 is here. I'm sorry, the maximum value of x1 is there. Here's the min. And here's the min. Here's the max. And so if I did what I suggested as a possibility, here is a range. Now, there we go. Here's a range then that you would allow yourself to do predictions of y in, relative to x1 and x2. What's the problem? Exactly. We don't know what's going on here. We don't have information there. If we don't have information there, should you use your model for prediction there? No. What happens if you now have variables x1, x2, x3, x4, and x5 in your model? How do you make this choice of what possible values that you can predict at? Figure out a way to graph stuff in 5 dimensions? There's a dissertation there if you can figure it out. Obviously, it becomes a lot more difficult, a lot more of a difficult problem. So what can we do from a practical standpoint? Obviously, a beginning point is always to look at the minimum and maximum values of x1, x2, x3, x4, and so on. Don't go beyond the minimum and maximums. What you can also do is use then these scatter plots as a way to look at, you could say bivariate or two-dimensional relationships, and make a judgment there as well about potential values that you can predict at. You can try the same for a 3-dimensional, but obviously it's going to be more difficult. So, this is somewhat some cautionary, I guess, some cautionary discussion here regarding prediction. And it's a difficult thing to figure it out. In fact, it's pretty much, I guess, impossible if you have a very very high dimensional set of, or very large number of predictor variables. Any questions? Okay. And finally, section 6.9 just simply goes over another example. Please make sure you read it in the book. Let's go to chapter 7 now. So chapter 6 and chapter 7 are introductions to multiple regression, when we have more than one predictor variable. Chapter 7 is going to talk about some additional topics where a lot of them focus on understanding the contribution of a particular predictor variable given you already have some other predictor variables in your model. This is important because there are going to be many situations coming up here where we might have, let's say, variables x1 and x2 in our model, and we need to make a judgment, is x3 really worthwhile to add to your model? Okay, one way to help make that determination is to simply look at sums of squares. We've looked at many different kinds of sums of squares in the past. In particular, we focused on 3 different ones. SSTO is your total sums of squares. In other words, if you didn't have any predictor variables at all, this is how you would, this is a measurement of how good you would do in your prediction by simply using, let's say, y bar to predict y. It's a measurement of squared error without any other predictor variables. SSE, though, is a measurement of squared error when you now incorporate your predictor variables of interest. Now, how much variability in y is left over once you have accounted for all these predictor variables. And then SSR, of course, is SSTO minus SSE, is a measurement then of how much you have gained then by using these predictor variables to predict y. Well, now what we're going to do is look at some other sums of squares to help us measure the effect of a particular predictor variable given some other predictor variables that are in the model. To begin with here, we have to look at a little bit of a slightly different notation. So SSE and then a parentheses with some predictor variables inside of that parentheses represents the SSE from a model that contains these particular predictor variables only. So SSE parentheses x1 is then the sum of squared errors using only x1 in the model. SSE of x1 and x2, well, let's use x1 and x2 only to predict y. Here's the SSE that we have. Now, hopefully you remember from previous discussions, in particular in chapter 6, as we continue to add variables, predictor variables to our model, our SSE is not going to decrease. You can't do any worse than what you had been, let's say, with x1 if you were to add x2 to the model. Can't do any worse. SSE is not going to go down. It's going to stay the same or go up. Remember, this corresponded to our discussion of r squared and the problems with r squared when we use the adjusted r squared. So SSE of x1, for example, is greater than or equal to SSE of x1 and x2. Now, where we can use that information then is help measure then the contribution that x2, in this case, has to your model if x1 was already in it by simply subtracting the two. Okay, this is going to be a number that's going to be greater than or equal to 0. So if x2 was very, very beneficial to the model when x1 is already in it, is this value here going to be small or large? Relatively speaking. It's going to be small or large.
What was the question?
If x2 was very, very important, very, very helpful to predict y when x1 is in the model, is this value going to be small or large? It's going to be large because this is going to be a lot smaller than this number. Okay? If x2 really doesn't help out much at all, is this value going to be small or large? It's going to be small. So you might think then that this is going to be very useful then to help determine, well, should x2 be in the model if I am already going to include x1? In fact, that's what we're going to use to help make that determination. This value here is going to be referred to as SSR. Why? Well, because we're looking at the contribution or the amount gained from using x2, given that x1 is in the model. So SSR of x2 given x1 is this reduction in SSE from using x2, given x1 was in the model already. We could also use the notation SSR of x1, which just means regression sums of squares with only x1 is in the model itself. Just to make sure you see this, and please note the little change to the notes. SSR of x3 given x1 and x2 in the model is just simply the SSE for the model with x1 and x2 only, minus the SSE for the model with x1, x2, and x3. That's it. So you can think of this as the extra sums of squares for y that are now explained by including x3 in the model, given x1, x2 were already in the model. Interestingly, one can show that if, in the case of x1, x2, and x3, if I take SSR of x1 plus SSR of x2 given x1 plus SSR of x3 given x1 and x2, add them all up, you get the regular old SSR that we've seen before for x1, x2, x3. So in essence, what we've done is partitioned our sums of squares. If you've taken a course like Stat 802, you've discussed stuff like this, where you partition your sums of squares. This is an example of that, doing that too. So that then, in our ANOVA table then, where we summarize these sums of squares, we can summarize it now like this, where we're used to seeing the regression row, we're used to seeing the error row, and the total row. Now I'm going to add rows corresponding to this partitioned SSR. Now note here that there are many other different versions of these SSRs that you could have. So for example, one could look at SSR of, let's say, x2 and x3 given x1's in the model. One could look at SSR x1 given x3. One could look at those two. It's just often it's convenient to go in numerical order, and that's why I did that there. Okay, so let's talk about now how we can use this information that we just learned about in section 7.1 to actually help us do a hypothesis test. What this hypothesis test is going to do, it's going to give us a formal way to make a judgment of, given x1 and x2 are in the model, is it really worthwhile to include x3? First, some terminology. Suppose we have two models of interest, a model A and a model B, for lack of a better name. We say that model A is nested within model B if model B has all the terms that are in model A. So everything that you see represented in model A plus something else. What I mean by term, I could be referring to, let's say, x1 or x2 or maybe x1 squared. That's what I mean by a term. And in particular, then, we often will refer to model A as a reduced model because it's smaller than model B. We'll refer to model B then as the complete model because it has everything that model A already has plus some other stuff. A lot of people will refer to the complete model as a full model. Our book uses complete model. So just some quick examples to make sure you're following the point here. Our A particular reduced model could include only x1 in it, and then a corresponding complete model includes x1, but also an additional term, x2. Alternatively, another complete model could have had, instead of x2 there, I could have had beta 2 xi1 squared as well. It just depends upon the context of what you're interested in. Another example. Suppose I have a reduced model of x1 and x2. One potential complete model could include x1, x2 plus x3, or another complete model could be x3 and x4. Again, depending upon the context of what you're doing. The main idea is that we have a name for the model that's smaller and a name for the model that's bigger in size. That's all. The one that's smaller always has to be, let's say, a subset of the one that's bigger. The reason being is because now we want to do hypothesis tests to compare the two models. So what we're going to talk about is what's called a partial F-test. Some people might call them a nested F-test. Our book calls it a partial. So we've talked about t-test before that allows you to test one variable at a time in a model. We've talked about overall F-test before that allows you to test all the variables at the same time. A partial F-test goes in between. And in fact, a t-test and an overall F-test are actually special cases of a partial F-test. You'll see why as we go along. So just to be general here, let's say I have the following reduced model in my HO. I have a model that includes up to G different variables. My complete model includes everything that we see in the reduced model plus some additional terms, all the way up to perhaps p minus 1 different predictor variables. So we can see how many additional terms does the complete model have. P minus 1 minus T. So I guess I have that kind of written there. So in essence, we could also restate our hypotheses like this. Null hypothesis is beta sub g plus 1 all the way up to beta sub p minus 1 is equal to 0. The alternative hypothesis is at least one of the betas in HO are not 0. I'm sorry, what?
These are not entirely equivalent.
Are they what?
The two statements are not entirely equivalent. Because
Why not? If you're making the assumption that you have a linear model such as this, they are.
I mean, in the first statement, the alternative states that basically every beta from g plus 1 to p minus 1 unequal to 0. And the second one states only at least 1.
Well, that's an interesting point there. But let's think of it this way. When you actually estimate the model, you're estimating this model or you're estimating this particular model, where you are allowing for the possibility that the beta may or may not be equal to 0. So you're allowing the possibility that these betas may or may not be 0. But you're restricting these definitely to be 0. So what do we use then as a test statistic? Well, this is where these sums of squares that we've been talking about come into play. Where, naturally, based upon the motivation I gave you before, you might say, well, let's take the sums of square error that we had for this reduced model and subtract off the sum of square errors for the complete model. So again, remember what we started off with talking about is that if this difference is small, then that says, well, these extra variables are not really reducing your sum of squares much. If this difference is large, then that says, oh, something's going on with these extra predictor variables. They're helpful. They're actually reducing your sum of squares by a lot. So we have this in the numerator to help us to take into account the number of extra variables that we're looking at, we divide by p minus 1 minus g. And in fact, in this numerator here, of course, these difference of these two SSEs is this SSR. SSR for xg plus 1 to xp minus 1 given x1 through xg are in the model. We can combine then this with what we're dividing by and call this, similar to what we have in the past, a mean square root due to regression. In the denominator here, we see what we had before with an overall f-test. All it is MSE for the entire model, for the model including all the predictor variables. So what we're doing is this. We are comparing then this gain that we get from these additional variables, the gain in terms of how we are reducing the sum of squared error, compared to the overall error from using all the variables. We call this F star. So that if this gain that we get from including these other variables is large relative to MSE, what's going to happen to F star? Is it going to be large or small? It's going to be large. I'd like to have some additional participation, please. If this gain is small, so meaning that this SSE here is quite similar to the SSE over here, meaning that the numerator is going to be small. What's going to happen to F star? It's going to be small as well. So how do we decide if we reject or don't reject HO? Look for large values of F star. Large values indicate, something's going on with these additional variables. They are helpful. If I include them in my model, I'm going to reduce my sum to square errors compared to if I didn't include them. And so that's an intuitive way to think about how this F star comes about. Of course, again, how large does F star need to be in order to say, yeah, we do have evidence, enough sufficient evidence to indicate that at least one of these other predictor variables is important? Well, that's where, of course, a critical value comes in, as it does in every other hypothesis test. Take the 1 minus alpha quantile from the F distribution with a numerator degrees of freedom of p minus 1 minus g. Notice where that comes from. It's right here. Notice how that's in the numerator of this big statistic. And the denominator degrees of freedom is n minus p. And that comes from right here. Decide if you reject or don't reject. Again, if F star is greater than the critical value, you reject. Set 5 your conclusion. If you reject HO, that says at least one of the variables are important in predicting Y, meaning that the complete model is better than using the reduced model. We have now scientifically proven that this is true. If you don't reject HO, well, there's not sufficient evidence to show that these predictor variables are important to predicting Y, meaning that the reduced model actually maybe better. Why didn't I say is better? Notice I said may be better.
Statements based on probability.
Well, somewhat, yes, but I need more. It just simply goes back to what you learned in your very first stat course about hypothesis testing. Can you ever conclude that HO is true in a hypothesis test? No. Why? Because your teacher told you? Why? Well, why can't you ever conclude that HO is true?
Because we don't have enough evidence.
Excuse me?
Because we don't have enough evidence.
What do you mean by enough evidence?
Like, maybe something missing in the model. Maybe we specify the model. Maybe, how can it be going?
I wouldn't say misspecified. Notice, and this is kind of an implicit assumption in any kind of hypothesis testing, you're assuming that that your model is correct in terms of the form of the model. You know, that we have a linear model. What's the probability of a type 2 error? Do I ever state this here? Okay. So that's why I don't have any kind of measure of, you know, if I say don't reject HO and say that HO is actually true, I don't have any measure of how good that statement is. So when you're talking about probability, it's kind of related to that. You know, maybe my probability of type 2 error is 1. Then I got problems. Okay.
It's never 0. That's why you never can say that HO is true.
Excuse me?
It's never 0. So that's why
Yeah.
you never can say
Yeah.
it's true.
Yeah. Well, it could be 0, but you don't know. You know, again, when you do a hypothesis test, the way hypothesis tests are done, you have to make an assumption to begin with that HO is true. And you know, especially if you're a stat student, and you get into mathematics behind why we do what we do in hypothesis testing, you are actually deriving a sampling distribution for your test statistic under the assumption that HO is true. If you're already starting off with that assumption, then it's kind of hard to say, I'm going to prove that HO is true. Can't do it. Okay. Suppose that there are only 3 variables under consideration, x1, x2, and x3. Here's the relationship of the partial f-test to an overall f-test and also a t-test. So let's say that I wanted to test beta 3. Is it equal to 0 or not? I could use a t-test for that. And notice what that says. Given x1, x2 in the model, is there sufficient evidence to say that x3 is important or not? That's what a t-test gives you. That's what we saw in chapter 6. Well, a partial f-test would do the same thing. You could do a partial f-test, get an f star. That will be equal to your t star from a t-test squared. Similar thing with the critical values. An overall f-test would test beta 1 is equal to beta 2 is equal to beta 3 is equal to 0. Well, we could also phrase this in terms of a partial f-test, where now look at the numerator here. The MSR for x1, x2, and x3 given nothing else is in the model. Let's take a look at an example. Again, this is with the NBA guard data set. This is on page 7.7. So what I like to do is determine if field goal percentage and free throw percentage, notice both are measurements of how accurate a player is in shooting the basketball, are important estimating PPM for the model that has MPG, height, free throw percentage, and field goal percentage in it. This is my complete model. So my reduced model only has MPG and height in it. So what do I need to do here? Well, let's actually go over to 10 here. First thing I'm going to do is estimate my complete model. And I'm going to need to get some sums of squares. And the easiest way to get sums of squares is to use the ANOVA function. You know, we've seen this a number of times before. I'm going to put the results into ANOVA.comp just to help me out. And we'll discuss the components of what's in the ANOVA function as we go along here. But the one thing I want to point out is this right here. Here's the SSE. So for example, if I said ANOVA comp $, the way that this object is structured, I can simply say quote SUM space SQ end quote. And notice how that just simply pulls out all the sums of squares, so that if I put 5 there, and am able to pull out SSE.
Are these the sum of the square that it gives in the ANOVA here, are they given the previous ones, basically fit in order?
Yeah, they are. Yeah, I'm going to address that shortly, but basically what I showed on page 7.3. Also what I'm going to do is estimate the reduce model within an object mod.fit.red for, I guess, reduce, and also pull out the corresponding sums of squares as well. Oops. Okay. So this is SSE for the model that has MPG and height. This is SSE for the model that has MPG, height, free throw percentage, and field goal percentage. So if I subtract the two, what do I get? SSR for free throw percentage and field goal percentage given MPG and height are in the model. So we can see that with these additional measures of how good a person shoots a basketball, what we are gaining in terms of these sums of squares is about 0.151 approximately. So using that information then we can form the F-star test statistic. So, as I had just shown you, here's one of the SSEs, here's the other SSE. I subtract the two to get an SSR given some variables in the model. I need to divide by P minus 1 minus G, just for extra reference here. We do a split screen. What I'm trying to do is form that particular test statistic. Actually, the one at the very top. So, what's P? Well, P is the number of betas in your model. What's an easy way to find that? Well, take the length of mod.fit.comp $coefficients. So that contains all your B's, your estimated betas. So how many, what is P here? P is 5. G in this case is 2. So how can I find that? Take the length again of mod.fit.red $coefficient and subtract off 1 because we don't need the intercept. We don't need to count the intercept. Then I can go back to ANOVA.com and pull out the mean square in a very similar way as I did the sums of squares, and so I get my MSE. F star ends up being 7.53. Set an alpha level of 0.05. I can then find my critical value using the QF function in very much the same way as we've done in the past. I get a critical value of 3.08. So notice that 7.53 is greater than 3.08. So we do have sufficient evidence from this sample that indeed at least one of these additional variables for free throw percentage and field goal percentage is important. I can also find the p-value, again using similar means to what we've done before, using 1 minus the pf function. So here's let me remove the split screen. So here's just then everything formally written out. You know, again on a test, I'd like you to formally write everything out to make sure that you understand what's going on. So I state HO, which is beta 3 and beta 4 are equal to 0. HA, at least one of the betas is not equal to 0. Step 2, I state my test statistic. Step 3, critical value. Step 4, test statistics greater than the critical value. And then step 5, your overall conclusions, which I've already said. Are there any questions? Now there's actually a little bit easier way to do this hypothesis test. And this is, we can use the ANOVA function again, but notice how we use it's different. I put in one of the model fitting objects that we had. You begin with the reduced model, and then comma, put in the complete model fitting object, and then say, do a test. Test equal F. Use an F test. And this is what I get out. Here's F star, and here's your p-value. Here's your SSR that we saw before. Here's the two SSEs as well. Here's P minus 1 minus G. Obviously, this is a lot easier. So, on a test, when time is important, which way would you do it? The way that I first showed you, or the second way? The second way. Okay? Why did I show you the first way? So that you can see how the actual test statistics formed. Questions? So one little other thing I want to show you with this use of the ANOVA function, just to make sure it's clear. Suppose I put the results of working with this ANOVA function into something called ANOVA.compare, for lack of a better name. And I do a names with it. And we can see the different components of this list. And so, for example, if I say ANOVA.compare $sign F, what ends up happening is that basically I get this column of information. So if I want, I can just say 2, and I get the actual F star value. But let's say that I work with this right here. I want to get the p-values. So you might naively try to do something like this. And I get an error message. The reason being is because since we are not using actual alphabetical or numerical characters here, R doesn't know how to interpret this part. Similar to what I showed you last week, I can put a quote around that part and pull that information out. In particular, there's the p-value. So, it's just a matter of working with the syntax. You just got to get used to it. Okay, page 7.9. I guess just a little side note here. Obviously in this class I take a lot of time talking about how to do stuff in R. And the reason why I do that is because, one of the biggest barriers to students, and then eventually people in the real world who are applying the stuff that they learn in school, one of the big barriers to doing statistics or even other stuff is how to use the software properly so that you can actually get the information you want. And so that's why I do take time to discuss stuff like I just did a minute ago. Okay. So what would happen if I actually ran ANOVA object equal mod.fit.com? What we saw was we got this output here. And let me actually just remove the split. What is actually being printed then right there? So notice we don't have the regression row as I had shown before in an ANOVA table when I had just typed it out myself rather than go to R. Well, what R is doing, and we kind of alluded to this a few minutes ago, is that it's basically doing this sequential sums of squares. Again, if you've done a Stat 802 course, you probably had come across this before, a sequential listing of sums of squares. Same kind of concept here. And notice the ordering that things go. Where I'm saying x1 is MPG, x2 is height, x3 is free throw percentage, and x4 is field goal percentage. This corresponds to the ordering that I used when I actually had estimated the model. So the way that R actually structures everything is in terms of the order that you put the predictor variables in that formula argument. And again, if I were to sum up all these SSRs, I get the overall SSR. This would be sums of squares due to your regression. Note that you also see some mean squares listed, an F test statistic value listed, and a p-value listed. So you might be thinking, okay, these are just doing the partial F tests, like what we had just discussed. So for example, you may think that this test statistic of 6.5 represents, given MPGs in the model, what's the benefit from adding height to that particular model, so that you would have height and MPG only in the model. That's what you would think. Unfortunately, that's not exactly true. So what I've written out here is that this is what you may think that ANOVA function is giving you in terms of the hypothesis test. But what it's actually doing is this. It's always in the denominator of F star using the MSE for a model that includes all 4 variables. So all the variables that you put in your mod.fit, I'm sorry, in the LM function, the formula argument, it includes all of them for the MSE. So that test then is not exactly a partial F test like what we had discussed. Just to show this to you, I actually went through the process of looking at the model with height and MPG only. Here's my p-value of 0.0179, and in this particular case, it's fairly close to what the ANOVA function gave us for the complete model. Any questions?
So the question is whether can you use this table to determine what parts to...
I would not use what R is giving you. What they're hoping is that this, by using the full model, by using the model that has all 4 terms in it, it's actually giving you maybe perhaps a better estimate of sigma squared. And so that's why they're doing it. But it's not really a partial F test. I would prefer not to use it. Maybe some others might disagree with me, but I would prefer not to use it. And another reason is this too, is that you have to have good reason to want to do tests like this in a sequential manner. Oftentimes there isn't, like in this particular case with the MD8 GAR data, there's not a good reason to do hypothesis tests in this sequential manner. Now there's another function, another ANOVA function in R. This comes in the CAR package. But notice it starts with a capital A instead of a lowercase a, as we've seen before. Remember, of course, R is case sensitive. So the capital ANOVA is different from the lowercase ANOVA function that we've talked about. And this capital ANOVA function actually typically gives you the hypothesis tests that are more of interest to you. In particular, consider the following scenario. With my complete model, I do a summary of the model fit object, and I just pull out that coefficients table that we normally see in the summary output. And what we have here are my usual t-tests. So for example, given that MPG, free throw percentage and fecal, given MPG, FTP, and FGP are in the model, what are the benefits from including height in the model? P-value is small, indicating, yeah, it looks like height is important, given the other variables are in the model. Well, what the ANOVA function gives you is this same kind of test. So if I say ANOVA mod.fit.comp, look at how these p-values are exactly the same. Now, this is especially of interest if you take any other stat courses. If you do other more sophisticated models than what we do in this particular course. In particular, my Stat 875 course, my categorical data analysis course. We look at more sophisticated versions of regression models. And in order to get a particular kind of test, to test the effect of a particular variable, we don't want to typically look at this kind of output because we get it ends up, without going into all the details, ends up giving us a different version of a hypothesis test than what this does. And this will be of more interest. I just used the word "this" a lot there. That probably wasn't very helpful, but you'll just have to take my Stat 875 class and know what I'm talking about. Or watch the videos. Anyway, so this is this extra ANOVA function could be helpful. And again, if you've had a Stat 802 course, you know that there's particular kinds of sums of squares, like a type 2 sums of squares, and that's a type 2 sums of squares. Section 7.3 is just a summary of the overall F-test, T-test, and partial F-tests. This is just there for your reference, just as a one-place summary, one location that summarizes everything. Note that on tests in the past, tests as in exams, I have actually had short answer questions where I ask you to compare and contrast these three different kinds of hypothesis tests. So just be aware that there might be a short question about that. Okay, page 715 then. We're going to talk about the coefficient of partial determination. We've talked about the coefficient of determination before. In other words, R squared. And what does R squared give us? It gives us a nice way to look at the reduction in our variability by including particular variables in the model. In other words, the proportional reduction in the variation of y achieved by using all the predictor variables in the model. Now, what we've been just talking about in this particular chapter are measures that are somewhat similar. These SSR measures. SSR of x2 given x1 says, given x1's in the model, how much are my sums of square errors going down if I include x2? So you might think, well, maybe I could come up with like a R squared like measure that gives me a proportion reduction in variability. And in fact, that's what we can do with the coefficient of partial determination. So for example here, it's kind of a weird notation, but this is what the book uses. R squared and then the subscript y. Just to remind you, your response variable is y. And then a 3 next to it say, suppose I'm interested in the reduction in the sums of squares by also including x3 in the model. The vertical line means given x1 and x2 are in the model. So again, R squared y3 given 1, 2 represents what's the contribution of x3 given x1 and x2 are already in the model. In particular, the proportion reduction SSE. So what does it look like for an equation? Now please be careful, this is a little bit different from our regular old R squared, because we're already starting from the standpoint of we have some variables in the model. So that R squared that we just looked at, this coefficient of determination I should say, is SSR of x3 given x1 and x2 in the model divided by SSE given x1 and x2 in the model. So in essence, this SSE given this SSE given x1, x2 in the model is playing the role of SSTO that we had with our regular old R squared. SSTO was the worst you could do if you didn't include any variables in the model. But now if we're saying let's include x1 and x2 in the model, what's the worst that we could do? SSE given x1, x2 in the model. And then in the numerator we put on top then, how much is gained from including x3. Just to make sure the point's clear. Suppose I look at r squared y3 given 2. What that says is SSR of x3 given x2 divided by SSE of x2. What's the numerical range of these coefficient determinations? Between 0 and 1. Okay, because we're looking at the proportion reduction. You remember, this SSE is always going to be less than this particular SSE. And of course the SSEs are all positive. So, if you're hoping, in this particular case, right here, if you're hoping that x3 is important to include in the model, you want your coefficient of determination to be as large as possible, as close to 1 as possible. If instead this coefficient of determination is close to 0, that says, okay, this x3 is not really helping out. Now, where is this used? And a lot of stuff that we're doing right now is leading up to Chapter 9. You're often given a particular situation where you have a bunch of predictive variables, and you don't know which predictive variables to include in a multiple linear regression model. And so what you're going to need to do is do what are called model building techniques to determine which variables and what form the variables should be in your model. Looking at a coefficient of partial determination is one of these model building techniques or procedures. You'll see shortly how this works. So, let's go back to the MBA GUARD data set again. Let's say that I already have MPG, height, and free throw percentage in the model. That's actually the model that we've been talking about. And we need to make a decision here. Is including age as well, or field goal percentage, good to do? So, that's where this coefficient of partial determination can help you.
How is this whole procedure different from looking at just R3?
It can be closely related. What we're going to do is look at multiple model building procedures. Looking at adjusted R squared is one. Looking at these coefficient determinations is one as well. They will not necessarily lead to the same model in the end. Okay, so what I need to do is this. Calculate both of these coefficients of partial determination. Notice the form here. The only difference between the two equations is this right here. X4 is field goal percentage, X5 is age. Now in R, there's not a convenient way to get these coefficients of partial determinations out. Instead, you're going to have to actually, let's say, get the components of the formulas and then use the formulas then to do the calculation. So, but the concepts are very similar to what we've talked about before. Suppose I look at a model that has field goal percentage in it. I call it mod.fit.comp1 as the end result. I use the ANOVA function to pull some stuff out to get the corresponding sums of squares. Mod.fit.comp2 now includes age in the model without field goal percentage. Again, I use the ANOVA function to get some stuff out. And then I also look at my reduced model, just like what I did before. Notice you do not see field goal percentage or age in it. Again, use the ANOVA function. And I'll let you look at the details on your own. I pull out the necessary sums of squares that I need and do the corresponding math. So the first one corresponds to field goal percentage. The second one corresponds to age. So if you had a choice between adding field goal percentage or age to your model, which would be better to do? Field goal percentage. It reduces your overall sums of square error that you had with just the 3 variables by 12%. Okay, that concludes that section. Section 7.5, you're not responsible for, but you're welcome to read it. And lastly, in Chapter 7, it's just a small chapter, Section 7.6. This is actually going to get at some stuff that we talked about at the very beginning of class. In particular, you want to avoid situations where you have 2 predictor variables that are highly correlated. So in an extreme situation, let's say you have x1 and x2. Those are the only variables in your model. And let's say they have a correlation of 0.99. Well, why would you want to include both of the variables in your model then? Well, you wouldn't. Because what x1 is telling you about the response is going to be basically just about the same as what x2 would tell you about the response. Because they're very, very, very highly correlated. And so we want to avoid having both of them in the model at the same time. Another reason is that computation problems can occur. For those of you who've had a matrix algebra class, remember this particular equation that we are using, that we learned about first in Chapter 5. If you've had a matrix algebra class, you know that there could be problems with finding an inverse of the matrix, depending upon the form of the matrix. You know, we need this x prime x to be non-singular. A singular matrix, you're not going to be able to find the inverse. You know, you could find, for example, a G inverse, if you've heard of those before. But you're not going to be able to find the inverse. When you have highly correlated variables, and they're in your X matrix, you can have problems finding this inverse. So you can have computation problems that can occur when you have highly correlated variables. And also, when they're highly correlated, this can cause estimates of the betas, in other words your B's, to be unstable from one sample to the next. And you'll see a dramatic example coming up. This whole idea of having highly correlated variables corresponds to what most people refer to as multicollinearity. We want to avoid having multicollinearity. So here's a dramatic example of this and the problems that it can cause. This is in my multicollinearity.R program. And all I did, just to demonstrate the problem, is I simulated some data where they are the predictor variables are highly correlated. So this is what I do. I set a seed so I can reproduce my results. X1, I just decide, let's let it be a sequence of numbers from 1 to 50 by 1. I just decided to do this for this particular example. No particular reason. X2 actually comes about through X1. So it's X1 itself plus a little bit of, you could say, noise. So that if I did core X1, comma, core X1, comma, X2, I have a correlation of 0.9999. I would say that's very highly correlated. My epsilon, what I'm going to do is actually simulate a y, as we did like in Chapter 3. My epsilon is going to come from a normal distribution with a mean of 0 and a variance of 100 squared. I'm going to get 50 of them. As notice how x1 has 50 values. I'm going to put this all together to find a y. So it's just an application of stuff that we first saw in Chapter 3. Again, there's my correlation matrix. So you would think that x1 is going to be helpful to predict y. You would think that x2 is going to be helpful to predict y as well. Again, notice the correlation between x1 and x2. And we could do a little scatter plot matrix just to demonstrate that. Obviously, notice x1 and x2. Quite dramatic. Let's actually estimate the models. Go over here to my notes. So first of all, I'm going to estimate the model with only x1 in it. Here's my B1, 5.66. Here's my t-test for x1. Is x1 important? Yes or no? Yes, it is. Small p-value. Well, let's also try a model with just x2 in it. Here's my B1. Notice how it's about the same. Here's my p-value for the t-test. Very small, saying x2 is very important. Well, let's try both x1 and x2 together. Notice how the b's change dramatically from what they were before. And in fact, now it says that I have a negative relationship between x2 and y. Of course, we know that's not true. Remember what my true model was. Look at my p-values. So this particular p-value says, given that x1's in the model, given x2's in the model, x1, there's not sufficient evidence to indicate it's important. This p-value is saying that given that x1's in the model, there's not sufficient evidence to indicate that x1's important. That x2's important. We know, though, that obviously x1 and x2 were used to construct y. This is what can happen when you have multicollinearity. You can have problems understanding, here as we see, the true relationship between y, x1, and x2. Also, let's see. Also, notice how these standard errors are extremely large now compared to what they were before. Now, just to emphasize that point, I simulated another data set. Did the exact same thing that we just got done doing, and there's my estimated model. Now, my model says that x1 has a negative relationship with y. Before, I had a positive relationship, and we do know that indeed it is truly positive. This demonstrates how the sample-to-sample variability, the effects that this can have when you have this high correlation. So what can you do? Well, don't use x1 and x2. Don't use both of them in your model. Use just one. There are other things that you can do too, but we're running out of time, so we will not discuss them. Well, let's keep on going. Sorry. I think it would be best for us to just finish out. We got 2 pages. I was thinking that there was more. Real quick, what happens if you go with the MDA GAR data set? Well, here's the correlation matrix. We saw a scatter plot before. It doesn't look like we have any high correlations here. And indeed, we don't really have any problems. What I'd like you to do on your own then is look at what happens when I sequentially estimate these models. First, I have a model with just MPG in it. Then I have a model with MPG and height. Notice how my estimate for MPG doesn't really change, even when I have height in the model. Compare that to what we had in the previous example when the B's were changing a lot. So when the B's don't change, this is a sign that you don't have multicollinearity problems. And you can see this as I continue to add free throw percentage, field goal percentage, and also age to the model as well. So I already talked about this first note. In Chapter 10, we will look at other methods to find when multicollinearity happens. because multicollinearity can also happen when, let's say, two variables combined in some way are basically a third variable itself. If you just look at a regular old correlation between two variables, that's not going to help you find that. Section 11.2 discusses ways to lessen the effect of multicollinearity if you want to actually include all the variables in your model. And lastly then, multicollinearity though does not affect predicting y or the confidence interval for expected value of y, prediction intervals for y. So if your goal is just prediction of y, and that's it, where you don't care about interpreting the effects that x1, x2 has on y, multicollinearity is not as bad of a problem to have, or not as big of a deal, I should say. Sorry to make you think that we were going to end a few minutes ago, and sorry to keep you over about 1 minute, but you get more for your money today. Any questions? Okay, that's it.